So last time we were looking at a Newton-Cotes formula, and we did one of n equals 1, and that actually gave us the trapezoidal rule. So the Newton-Cotes formula was to actually use the Lagrange interpolating polynomial and then use that to integrate when we want to try to find the integral of f. And so we did the derivation when n equaled 1, and we ended up with an error formula that shows us the error is minus f double prime at some c that's between b and a over 12 times b minus a cubed. So now we are doing a derivation for n equals 2. And for n equals 2, again, we approximate f of x by a quadratic. So we approximate f of x by a quadratic passing through the point a, f of a plus b over 2, f of a plus b over 2, and b. F of b. Okay, so here x naught is a, x1 is a plus b over 2, and x2 is b. So I is the integral from a to b of f of x dx. But now we're approximating this by the integral from a to b of the polynomial p2 of x. Now we already know what that looks like. We've actually figured out what that polynomial is. This is the integral from a to b. We're going to have L0 of x times f of x naught plus L1 of x times f of x1 plus L2 of x times f of x2 dx. And so like we did before, we pulled the f naught out, f of x naught out, and that gave us the integral from a to b, and the first polynomial was x minus x1 times x minus x2 divided by x naught minus x1 times x naught minus x2 dx plus dot, 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 all the way to the last one. Okay, so after we do that, we get Simpson's rule. So we ended up getting, with some work, we get f of a plus f of a plus b over 2. And there's a 4 in front of it. That looks awful. 4 times f of a plus b over 2 plus f of b all over 6 times b minus a plus the error we incur with the approximation. So what does our error look like? Well, our error you have f of x is Pn or P2 of x And the error looks like the third derivative of x over 6 times x minus a times x minus a plus b over 2 times x minus b. Okay. So the error and the integral is the integral from a to b, and we need to integrate that thing. So that's the third derivative of x. I'm sorry, that should be at c, not at x. That's at some value c, not at x. My apologies. Okay, and this is over 6. And then you're integrating a cubic. Okay, so this is x cubed. So this is x cubed plus stuff all the way down to the last term, which is minus a times a plus b over 2 times b dx. And so end up with something that is actually, oh, I really need to leave. Let me put it back the way I had it. I'm sorry. I'm gonna write the whole thing. X minus a times x minus a plus b over 2. Why do I keep saying plus? I'm sorry. I mean, plus meaning I'm adding these terms on to the expression, but I'm multiplying them. X minus b dx. And so this ends up being something of order b minus a to the 4th power. So it's O of h to the 4th. Okay. So okay. By approaching this problem, another way, a higher order term involving f, the 4th derivative at c, can be derived. Okay, and I'm going to choose not to do that right now. But in this other way, we can show that the error is minus b minus a to the 5th power over 90 times the 4th derivative. Interesting, I wrote it like that over here.
Oh. Excuse me, ma. Is it to the 5th or 4th power?
Pardon?
Is it to the 5th or 4th power?
This one is to the 5th.
Okay.
So there's another, there's another technique that you can use to show that the error goes like that to the 5th power.
Oh, okay.
Yes. Okay. All right. So this, oh, I forgot to point it out. Dun, dun, dun. This was Simpson's rule. Okay, so when n equals 2, you get Simpson's rule. All right, so here's our summary. So for the trapezoidal rule, you get the integral from a to b of f of x dx is equal to b minus a over 2 times f of a plus f of b plus f of a.
Excuse me.
Yes.
Sorry, ma, but you wrote IV.
I wrote what?
F of IV.
Yeah, that is the fourth derivative,
Okay.
but it's
Oh,
yeah. So remember back here, it was the third derivative. Remember, this one was the third, that was the second derivative,
okay.
but it was at h cubed because we had divided by an h. So,
Okay.
and then here, this one is the fourth derivative, but it's b minus a to the fifth.
Okay.
Okay. Yes.
All right.
I know it looks weird, but that is correct.
Okay.
No problem. I'm fine with your questions. I appreciate your questions because if it's wrong, I need to know.
Okay.
And then this one is minus h f double prime. Let's see, over 12 times h cubed. And then a less than c less than b. And this is exact for f of x of degree 1 or less. And that makes sense. If the f of x is degree 1, that means you just have a slanted line, which is going to give you a perfect trapezoid, and a perfect trapezoid would have no error. So exact for f of x of degree 1 or less. And then Simpson's rule. That is the integral from a to b, f of x dx is going to equal, why did I write b minus a? Let me just write h over 2. And I'm going to write this as h over 3 times f of a. Why do I feel like I wrote something wrong? Oh no, that is 6. All right, is it a 3 or is it a 6? Trying to remember. It's a 6. Okay. I have a 3 in my notes, but it is a 6. Okay, and this is 4f of a plus b over 2 plus, oh, I know why, because h is here, h is h over 2, so that's why it was a 3, but it's okay, yes. This is f of b, and then its error is minus the 4th derivative at c all over 90 times h to the 5th. And this is exact for f of x of degree, and I should say, this is not f of x, this has to be a polynomial. Degree 3 or less. Okay, so now the trapezoidal rule, you guys can see that we only did the trapezoidal rule where we had the integral from a to b, and we didn't divide it up. When we divide it up into smaller intervals and we have like n intervals, that's when we're going to have the composite trapezoidal rule. And the composite trapezoidal rule, its error is not quite as good as the trapezoidal rule, but it's not bad. Okay, so other rules. This is n equals 3. Okay. My notes got out of order. Two was Simpson's rule. Midpoint rule, trapezoidal rule. 3 was Simpson's rule. Newton-Cotes formula. 1, 2. Summary was supposed to be 3. And this is 4. Okay, so suppose n is equal to 3. Okay, so now I have I is equal to the integral from a to b, f of x dx. And this is the integral from a to b of the sum I equals 0 to n of f of xi times the weights wi. Okay, so we can do this, and we can even just start off with the first one being w naught. As we know, it's going to be the integral from a to b of L naught of x dx. And that's going to be the integral from x naught to x3. And now we have to put in, so we're going to get x minus x1 times x minus x2 times x minus x3 divided by x naught minus x1, x naught minus x2, and x naught minus x3, integrating that whole thing dx. Now, we're going to pull out each one of these we know is h. So let's just pull those h's out. So when I do that, I get -1 over 6h cubed. Now, why am I trying to get that? did the 6 come from? I'm not sure yet. I honestly am not sure. We're going to keep going until I figure out where I got it from. And this is x minus x1 times x minus x2 times x minus x3 dx. I'm still trying to figure out where it came from, guys. Okay, so now I'm going to do a substitution. So I'm going to let u equal x minus, what is my substitution? I'm going from 0 to 3. And then I have u minus 1 times h times u minus 2 times h times u minus 3 times h times h du. Cannot remember. Okay, this gives me minus h over 6, the integral from 0 to 3 of u minus 1 times u minus 2 times u minus 3 du. And miraculously, this becomes 3h over 8 without me not even remembering how I got that. But after you find W1, W2, and W3 and put it all together, you get I is equal to the integral from A to B of f of x dx is approximated by 3h over 8. And you're going to get f at x naught plus 3 times f of x1 plus 3 times f at x2 plus f at x3. Okay, sorry guys, my back started hurting. I had to stand up. Okay. All right, so that's what we get. So that's what happens when n equals 3. All right. One other rule, very simple rule, the midpoint rule. Okay, so that's the integral from A to B of f of x dx. And that is equal to, very simple, we talked about this, b minus a. You just take f at a midpoint, f of a plus b over 2, and its error, which I'm just going to give to you, is b minus a cubed f double prime at eta over 24, where a is less than eta is less than b. Okay. So the question now is convergence. All right. So as I take this integral and I let n, we add more and more intervals, does it converge? Okay, so let's just talk a little bit about convergence. Okay. So does In of f, that means now I have n intervals. Does this thing actually go to the true value of the integral? As n goes to infinity? And the answer is not always. Okay, so not always. Okay, so one particular interval that we can show will not work, and is the integral from -4 to 4 of 1 over 1 plus x squared dx. Okay, so actually, as you start adding n, like we're getting ready to do now, it will diverge. Okay, so now what we just talked about was very simple. That was just taking an interval and writing it, just starting with b and a and making a trapezoid, or making a parabola go through and using a trapezoidal rule, Simpson's rule, midpoint rule, even that other Newton-Cote formula I derived with n equals 3. All of those we've only done with just one whole block interval. And so now what happens is, what happens if you divide this thing into several intervals? Okay, so now we're going to do the composite quadrature rule. Okay. So D is going to be composite quadrature rules integration. All right. So we're going to use, so the technique, I'm going to use, this is used for large intervals. So if your interval is large, you're going to try to maybe break it up to improve accuracy. Okay. All right. So something very simple. So for example, i.e. N equals 2, that's Simpson's rule. We already know that. We already know that the error is equal to the fourth derivative, negative fourth derivative at c over 90 times h to the fifth. And you can see that can be large. If h is large. Okay. So it may just take over and you have mostly error. Okay, so the remedy to having a large error is to subdivide the interval into a partition of smaller intervals. Okay. All right, so let's do this thing. All right, here's a picture. Function. Right. I want to go from A to B. And then I'm going to split it up into smaller intervals. Okay. So this one's going to be x0, x1, x2, x3, xn minus 1, xn. Okay. Now, okay. Here's the example. And we have the integral from 0 to 2 of e to the x dx is 6.3890561. I might even be able to get it better than that. So let's see. That's e to the 2 minus 1. So clear. Second function, e to the 2 minus 1 equals. Okay, 6.389056099. Yeah, I told you I could get it a little better than that. All right, so now if I use Simpson's rule, and I just do the integral from 0 to 2 of e to the x dx using Simpson's rule, then I'm going to get 6.4207278. And so my error is equal to minus 6.4207,278. So I get 0.031671701. Okay. But let's suppose I do it with two intervals. So I'm going to split it up. So I do the interval from 0 to 2 of e to the x dx. But I do a 0 to 1 interval of e to the x dx using Simpson's rule. And then I do a 1 to 2 of e to the x dx. I actually get 6.3912102. And so now my error is 0.0021541. Okay, so just by splitting it up, okay, my H went from H to H over 2, and my error went from error to 1 over 32 times the error. So just by dividing it in two intervals, I was able to reduce my error by 1 over 32. Okay, so let's talk about the composite Simpson rule. The composite trapezoidal rule. Oh, I do that after I do composite Simpson rule. Okay.
Excuse me, ma.
Yes.
The example, the Simpsons rule, I didn't get what you explained there.
Okay, so I'm getting ready to show you how I got that.
Okay.
So what I did was I originally started for the example, I originally started out like this.
Okay.
So we had from 0 to 2 of e to the x.
Okay.
So this is what we had from 0 to 2 of e to the x. And so we applied Simpson's rule just on this whole interval. So we took between 0, 1, and 2.
Okay.
We fit a quadratic to this. And when we fit a quadratic to this and we integrated the quadratic, we got the value of this.
Okay. Okay.
So now in the second thing, I split the interval in two.
Okay.
So now I got a point here, and then I got a point here. And so now I did my quadratic on this piece and integrated, and then I did a quadratic on this piece and integrated and added them together.
Okay.
Okay.
Yeah.
Good.
Mm-hmm.
Is that clear to everybody?
Yes.
Okay.
Yes.
Good. Okay. So now for Simpson's rule, you must have an even number of intervals. okay? So from here to here, that's 2h. From here to here is another 2h. From here to here is 2h. Okay, so from x, so this is 2h, this is 2h, and this is 2h. Okay, so now we're going to do I, the integral from a, which is x naught, to b, which is xn. So, oh, actually, I think I did, yeah, xn of f of x dx. Okay, so without loss of generality, I'm going to let n be 6, just so you can get an idea of what's going on. Okay, so if n is 6, I'm going to get, I still get h over 3, because h is equal to h over 2 in this problem. So here, if you let the h is really, yeah, h. Okay. All right, so now we're going to take, oh, I need, you know what? I'm going to fix my picture. Let me just fix my picture. Okay. So now I'm going to use Simpson's rule on this part. Then I'll do it on this part. And then I'll do it on this part. Everybody see what I'm doing? So when I do Simpson's rule on that first part, I get h over 6 f at x naught plus 4 f at x1 plus f at x2 over 6. So that's the first part. But then I get f of x2 plus 4 times f of x3 plus f of x4. So that's the second part. Then I get plus f of x4 plus 4 times f of x5 plus f of x6. And that is the last part. So as you can see, just doing the composite Simpson's rule for n equals 6, I end up with h over 6, and now I get f at x naught plus 4 times f of x1 plus 2 times f of x2 plus 4 times f at x3 plus 2 times f at x4 plus 4 times f at x5 plus 1 of f of x6. Okay. So that is what I get. So in general, I is equal to the integral from A equals x naught to B equal to xn. And again, n is even of f of x dx. That is equal to h over 6 times f at A plus 4 times the sum I equals 0 to n over 2 of f at x sub 2I minus 1. So that's all the odd ones. So 4 times everything that's odd plus 2 times the sum I equals 0 to n over 2 minus 1 of f at x sub 2I. So that's all the even ones plus f at b. And then I still have my h to the 5th over 90. But now I have the sum of these errors. The sum I equals 1 to n over 2 of the 4th derivative at c sub I. And here h again is b minus a now over n. Why am I confused? H is b minus a over n. Is it 3 or 6? It's making me mad. I gotta go back and look. I'm gonna have to go back and look. 2. Okay, so the composite trapezoidal rule. This one is just as easy to come up with. All right, you do the same thing. The only difference is for this one, still h is b minus a over n. And you're still going to take your interval. Okay. So now one of these is h. Okay. So now we're going to, let's say we did the same thing, but this time we only do, we're going to do 6. Where's the n equals 6 back here? We're going to do that picture. Yuck. I'd rather mess this one up again. Okay, same thing again, but this time we're using the trapezoidal rule on each interval. So every interval gets its own. So I have 1 and then 2, 2, 3, six. Why do I have, oh, because that green one wasn't supposed to be shaded. Like, why do I have 7 intervals? Here we go. Okay, and this is B. Okay, so we're going to do the trapezoidal rule on each interval. Okay, so if you guys are not quite sure, that means you want to start here, and we're going to make trapezoids. Okay. All right. So I is equal to integral from A to equals x naught to B equals x6 of f of x dx. And so now that's going to be equal to h over 2. And then we're going to have, this is long, f. I'm not going to write it all out, x naught plus f at x1. That's the first one. Then we're going to have plus f at x1 plus f at x2. That's the second one. Plus f at x2 plus f at x3. So that's the third one. Plus dot plus f at x5 plus f at x6. And that's the last one. So now, if I look at this, this turns out to be h over 2, f at x naught plus 2 times f at x1 plus 2 times f at x2 all the way up to 2 times f at x5 plus f at x6. All right. So in general, I is going to equal the integral from a equals x naught to b equals xn of f of x dx. Going to be h over 2, and then you're going to get f at a plus the sum I equals 1 to n minus 1 of 2 times, and put a 2 in front, f at xi plus f of your last element, f of b. Okay? And your error is minus h cubed over 12. The sum I equals 1 to n of f double prime of c sub I all over, oh, I took the 12 out already. Yay. Yay, we're on to something nice, something different. Not one of my favorite things. Gaussian quadrature. Okay, Gaussian quadrature. I like it. For one, we learned trapezoidal rule and Simpson's rule in calculus. So by the time you get to do it here, you're either going to be doing it like I just do it, or you're going to be heavily inundated with hard theorems, which I could put in here, but they're not all that helpful. So I didn't bother. Okay. So, oops, I went black. For the composite Newton cotes, formulas, the function is evaluated at equally spaced points. So you take your interval n, you divide it by h, and you are set with all of your intervals that are all the same, equally spaced away from each other where your x's. Okay. If the xi's are equally spaced, if the xi's are not equally spaced, this restriction, okay, I'm sorry. If the xi's are equally spaced, this restriction can significantly decrease the accuracy of the approximation. Okay. So Gaussian quadrature chooses the points for evaluation. So Gaussian quadrature in fact, they're already been chosen. You don't even know the integral, but your quadrature points have already been chosen for you. Okay, so Gaussian quadrature chooses the points for evaluation in an optimal rather than equally spaced manner. Okay, so we're going to approximate an integral I equal to the integral from a to b of a function f of x dx. And this thing is going to be approximated by a sum I equal 1 to n of sum ci times f of xi. Okay? So the nodes x1, x1, x2, all the way up to xn, and the coefficients C1 through Cn are chosen to minimize the expected error. Okay. All right, so here's the derivation for n equals 2. All right, so this is actually rather cool. I really like this. So we're going to do the integral from -1 to 1 of f of x dx is going to be C1 f of x1 plus C2 f of x2. Now, in this derivation, I have to find C1, C2, x1, x2. All right, so there are 4 parameters, all right, to be chosen. Okay. All right, so let's suppose that f of x looks like a naught plus a1x plus a2x squared plus a3x cubed. Okay, so we want to choose, so our goal is to choose x1 and x2 and c1 and c2 so that the formula is exact. Okay. So what is that actually equal to? So the integral of -1 to 1 of a naught plus a1x plus a2x squared plus a3x cubed is actually equal to a naught, the integral of dx, plus a1 over 2 x squared plus a2 over 3 x cubed. Oh, I'm sorry, I'm already integrating. Stop it, Dawn. Stop it. I'm moving too fast. Moving too fast, too fast. This should be A1, the integral of x dx, plus A2, the integral of x squared dx, plus A3, the integral of x cubed. Okay. So now f of x is equal to 1. So let's say f of x is equal to 1. Then the integral from -1 to 1 of f of x of 1 dx is just equal to 2. Okay? So that's what f of x equals. Okay. But if I go back to here, that integral says c1 times f of 1 plus c2 times f of 2 has to be that value. So that has to equal c1 f of 1 plus c2 f of 2, f of 1, no, c1 f of, right, the formula is 1. So it doesn't matter whether I, yeah, f of 1, f of x1 plus f of x2. But f of 1 is 1, and f of x2 is also 1. So I just get that. So now I have 2 is equal to c1 plus c2. Okay. So now if f of x is equal to x, then I get the integral from -1 to 1 of x dx. But that's just 0.
Excuse me.
Yes.
Excuse me.
Yes.
The C1 F of 1, is it supposed to be F of 1 or S1?
It should be x1. Thank you.
Oh.
Okay. So now 0 has to equal c1 f of x1 plus c2 f of x1 again, x2. So that's c1 x1 plus c2 x2. So now I get 0 is equal to c1 x1 plus c2 x2. Okay. F of x equal to x squared. So I get integral from -1 to 1 of x squared dx. And that integral is just 2/3. Okay, but that has to equal c1. F of x1 is going to be x1 squared plus c2, and f of x2 is just going to be x2 squared. So now I get 2/3 has to equal that. Okay, and then the last one is f of x is equal to x cubed. So I get the integral from -1 to 1 of x cubed dx. And again, I'm going to get 0. But this has to equal c1 times x1 cubed plus c2 times x2 cubed. Okay. So now you solve all four equations for C1. So we have four equations and four unknowns. So we solve using algebra for C1, C2, X1, and X2. And we find out that C1 is 1, C2 is 1, X1 is -1 over the square root of 3, and X2 is +1 square root of 3. So therefore, I get my integral I equals the integral from -1 to 1 of f of x dx turns out to be approximately f of -1 over the square root of 3 plus f at +1 over the square root of 3. All right. So this gives the exact result for a polynomial of degree 3 or less. But you would never guess how good this approximation is, even if it's not a polynomial of degree 3 or less, if it's another kind of function. So we're going to pick up here and figure out how to do the other Newton-Cotes formulas, show you how to integrate something that is not on the integral from -1 to 1, show you how to integrate something that's an improper integral. I love those, they're wonderful. And then the last thing we'll do in this section is Romberg integration. And I think about that time you guys will have another test. Okay, good to go.
Thank you.
You're so welcome.